In this video, we'll be taking a look at how volume changes can affect equilibrium by causing shifts in certain directions. So remember that volume changes are really for gas systems only. And that's because the gas is affected by pressure. Remember from the relationship PV is equal to nRT. And so here we have gas systems. And so if we change pressure, this will lead to an equilibrium shift that will try to sort of relieve or change whatever the pressure was, change was that we did. So let's just start off with a basic reaching equilibrium graph. So let's assume we only start off with reactant. We'll have only reactant at the beginning, and that'll drop down until it stabilizes because it's being used up. And then at the end, we're going to have some, not at the end, but we'll have product form. And so that's going to show an increase until it stabilizes. So we'll have our O over here, our O2 over here. This is our SO3. And then our H2O, let's just say, is over here. It likely started off at zero. SO2 also over here. It started off as 0 as well, but I'm just showing the lines separate so that way you can see what the changes are. So here's my SO2, like that. And so what you'll notice is that the change for the SO3, losing SO3 happens by minus 2x because there's a coefficient of 2. The oxygen plus 1x because there's a coefficient of 1, and the SO2 formation plus 2x because there's a coefficient of 2. And so we've reached equilibrium at the point where the concentrations have stopped changing. Let's just say around there. That's our equilibrium. And now we're going to introduce a stress to it to disrupt that equilibrium. And our focus is going to be to change the pressure in some way. And how do we change the pressure? Well, we have to do it by volume. Adding inert gases will not do this, will not affect the equilibrium because you do increase the overall pressure when you add inert gases. However, you're not causing more collisions between the reactant particles. You're just causing more collisions between particles and the inert gas, but not between the reactant particles. So the stress we're going to do here is we're going to increase the volume. And if we increase the volume, what that means is that we've actually lowered pressure. So we want to undo that. We want to undo the lowering of the pressure. So we want to undo the lowering of the pressure. So we have to undo the lower pressure, we need to increase pressure. Increase pressure by shifting to the side that has more particles. So how do we know that? Well, we can take a look at our equation. This side here only has 2 particles of gas, or 2 molecules of gas. This side here is 1 and 2, so this is 3 molecules. So since I increase volume and therefore decrease pressure, I want to increase the pressure again. How do I do that? Well, let's shift more to this side here where there's more molecules of gas, therefore more pressure. So we're going to shift to the right. Shift left to right. Now, with pressure changes, as soon as you increase the pressure, you would see a sharp increase for all gases because their concentration has changed. If you decrease the pressure immediately for all the gases, all the substances there, you would see a sharp decline. So that's how you know you have pressure changes. All of them will experience either a sharp decline or sharp increase. So here we decrease the pressure. So technically that's like the concentration of the gases being reduced right away because they have more space to swim around in. So they'll see a sharp decline at first, just a vertical line, and then we can do our gradual changes as we go. So, and this won't go down to zero. It's a bit above zero, so it's not touching the zero line. So let's make our shift happen. So if our shift happens, that means that the SO3 is being used up because we're going towards the right side. Until it flatlines and we're at equilibrium. The SO2 and O2 are being produced. So O2 will go up until it flatlines. And SO2 will go up as well until it flatlines. And remember that the change that happened here was about plus 1x because O2 is just 1. The change that happened here was plus 2x because SO2 has a 2 in front. And the change that happened here was about minus 2x, whatever number of moles it was relative to the others, because the 2 is in the front there. But the point is that because we saw a decrease in pressure immediately, there was a sharp drop for all the substances in their concentration. Pressure and concentration can be viewed as similar things when it comes to gas systems. And then afterwards, we had a gradual increase for our products since we went to the right and decrease for our reactants since we went to the left. So let's try one more example. And let's actually show where our equilibrium is. So our new equilibrium basically happens when everything flatlines together. So this is the new equilibrium. With the same K. The K does not change. So when the new equilibrium reestablishes itself, the K will be the same as it was before. Okay, so now we'll introduce a new stress just to see what it looks like. So let's go ahead and do a new stress here. We're going to, let's reduce the volume. So if we reduce the volume, what have we done? We've increased the pressure. So to undo, we need to reduce the pressure, because that's the opposite of increasing the pressure, by shifting to the side that has fewer particles, because fewer particles means less pressure, less collisions. So we're shifting, what side has fewer particles? Let's go take a look. Shifting from, let's see, so fewer particles on this side because there's only 2 versus 3, so shifting from the right to the left. So shifting from, let's just do this symbol here, right to left. So in this case, we're going to be going the other way now. We'll be using up SO2 and O2 to make SO3. So our SO3 will rise and SO2 and O2 will go down. But before we do that, remember we increased pressure. So that means automatically all the gases will experience a jump in their molarity, in their moles per liter, because now they're in a smaller space, right? That's one of the differences. You're not adding anything, but you're still seeing that jump in molarity because now you have less space for them to swim around in. So let's go ahead and do that. We'll do there's going to be a jump here. I'll do a different color for this. There'll be a jump over here because there's more pressure, jump over here, and then a jump over here for all of them. And then we can show a gradual consumption or production as we see fit. So remember the SO2 and the O2 are going to drop. So SO2 will drop until it stabilizes again. O2 will drop as well because we're using it up until it stabilizes again. But the SO3 is being produced now because we want to reduce the pressure. So that's going to go up until it stabilizes again. So here there was an increase of about, let's say, plus 2x, whatever number of moles times 2 compared to oxygen, for example. Here for the SO2 was minus 2x, and here for the oxygen it was minus 1x. So the equilibrium reestablished itself once everything sort of flatlined. Again, I'm not very accurate here. If I had numbers, it'd be more accurate, more precise. But this is our new equilibrium. With the same great K. same K as the previous ones, because it did not affect our equilibrium constant. It did cause a shift, but then we readjusted and readjusted, and that was in order to readjust, to reestablish our equilibrium and get the same K. So even though these concentrations might be different from what we had maybe over here, for example, or over here, when we do our K calculation, the ratio will end up being the same. So we'll have the same K overall. So in this video, we saw the effect of pressure on the shift of an equilibrium. And when we say pressure changes, it's really in relation to a volume change as opposed to adding an inert gas. If you did an inert gas, there'd be no change. It wouldn't knock it out of equilibrium. There'd be no shift. It would just continue in a straight sort of flat line all the way if we were doing inert gases instead. So what we saw here is that one of the main differences, though, is that when we changed the volume and therefore the pressure, all of your substances initially experience either a sharp decline or a sharp drop. A sharp decline or a sharp increase. The decline is if we lowered the pressure at first as our stress, and the increase is if we increase the pressure at first as our stress. You would not see that for something where you're adding one particular concentration or one particular substance or removing one particular substance. You'd only see it for that one thing that you're adding or removing, but not for everything else. Everything else would be gradual. And then temperature, everything is gradual. And then for pressure, well, everything starts off with a sharp increase or decline. And so those are some tips and tricks you can use to figure out what type of system you're dealing with just by looking at the graph. In the last video for this lesson, we're going to take a look at the effect of adding a catalyst to the equilibrium system.